Welcome back. There's a mystery at the heart of our solar system that's been driving scientists crazy for decades. Imagine a planet that breaks every rule in the book, a world where computer simulations say, this can't exist, but reality says, here I am anyway. That's Mercury. And here's the crazy part. When researchers run thousands of planetary formation simulations, they produce 0 Mercuries. 0, not 1. This tiny world orbiting just 58 million kilometers from the Sun has an 85% iron core when it should have 50% maximum. It contains water ice and volatile chemicals when a giant impact should have vaporized everything. And scientists are now calling it the biggest unsolved mystery in our solar system. So, in this video, I'm going to show you exactly why Mercury shouldn't exist, what violent catastrophe might explain it, and why the BepiColombo mission arriving in November 2026 could rewrite the textbooks on how planets form. Let's dive into the crime scene. Let's look closer at the data. Mercury is the smallest planet in our neighborhood, with a diameter only slightly larger than Australia. It is a world of extremes. Orbiting at an average distance of just 58 million kilometers from the Sun, it endures a thermal battering unlike anything else in the solar system. On the day side, surface temperatures soar to a lead-melting 430 degrees Celsius. Yet, because Mercury has virtually no atmosphere to trap that heat, the night side plunges to a freezing minus 180 degrees Celsius. It is a world of fire and ice, quite literally. But the real mystery isn't its weather, it's its very existence. To understand why, we have to look at the standard model of planet formation. Picture the early solar system, a swirling disk of gas and dust surrounding the young sun. In this accretion disk, dust grains stick together to form pebbles. Pebbles become boulders, and boulders eventually smash together to form planetesimals. Over millions of years, these bodies grow into the planets we know. This model works beautifully for Earth, Venus, and Mars. It explains the gas giants. But when you plug the data in for the innermost region of the solar system, the model breaks down. There simply shouldn't have been enough material that close to the Sun to form a planet. And even if there were, the gravitational interactions with Venus and Earth should have either flung it into the Sun or ejected it from the system entirely. As planetary scientist Nicola Tosi of the German Aerospace Center recently noted, Mercury is a major unresolved problem. It is an anomaly that refuses to go away. And this isn't just a minor discrepancy. It is a fundamental contradiction that suggests we are missing a huge piece of the puzzle regarding our own origins. If you want to stay updated on this unfolding story and other deep dives into the mysteries of our universe, make sure to hit that subscribe button. We're tracking the BepiColombo mission closely this year, and you won't want to miss what comes next. Now, let's return to the surface of this enigma. Recent flybys, including the one performed by the BepiColombo spacecraft in early 2025, have given us high-resolution views of a surface that tells a violent story. We see ancient lava flows, vast plains of solidified magma, and heavy cratering. But we also see something else. Wrinkles. These are lobate scarps, cliffs that stretch for hundreds of kilometers, formed as the planet's interior cooled and contracted over billions of years. Mercury is literally shrinking, shriveling up like a drying raisin. But the surface features are just the skin of the beast. The true anomaly lies deeper. Mercury is incredibly dense. In fact, it is the second densest planet in the solar system, just behind Earth. But Earth's density is partly due to its sheer mass compressing its interior. Mercury is tiny. For it to be this dense, it must be made of something incredibly heavy. This brings us to the iron core problem. Standard planetary models predict that a rocky planet should have a core that takes up about 50% of its radius. Earth fits this, Venus fits this, Mars fits this. Mercury? Its core occupies a staggering 85% of its radius. It is essentially a giant ball of iron with a thin veneer of rock painted on top. This structure is radically different from anything else we see. It suggests that Mercury is not just a failed Earth or a smaller Venus. It is something else entirely, a freak of nature, a cosmic accident. The implications of this are profound. If our standard models can't produce a Mercury, if, as dynamicist Sean Raymond puts it, simulations produce 0 Mercuries, then our standard models are wrong, or at least they are incomplete. We are missing a mechanism, a violent, catastrophic, or perhaps subtle mechanism that operated in the chaotic dawn of the solar system to sculpt this iron world. As we move forward in this investigation, we are going to dismantle the leading theories one by one. We will look at the violence of giant impacts, the chaos of planetary migration, and the baffling presence of chemicals that, by all rights, should have boiled away billions of years ago. Mercury is not just a rock, it is a crime scene, and the evidence is scattered across 58 million kilometers of space, waiting for us to piece it together. The suspect list includes rogue planets, the Sun itself, and the chaotic dance of gravity. In the next chapter, we will dive deep into the density dilemma and explore why the 0 Mercuries problem is keeping scientists up at night. We will examine the mathematics that say this planet is impossible and the physical reality that proves it is there. As we established in the previous chapter, Mercury is an anomaly. It is a planet that, according to our best simulations of the early solar system, should not exist. But it does exist, and its physical properties are taunting us with a riddle that is written in iron and rock. The core of the problem, quite literally, is density. To understand why this is such a headache for planetary scientists, we need to talk about how planets are built. In the standard accretion model, the ingredients available to build a planet depend on how far you are from the star. Close to the Sun, it's hot. Volatiles like water and gases boil away, leaving behind silicates, rock, and metals, iron, and nickel. Further out, where it's cooler, you get ices and gases. Based on this, Mercury should be a rocky world similar in composition to Earth or Venus, perhaps a bit richer in metal, but broadly comparable. It should have a metallic core surrounded by a thick mantle of silicate rock. Here is the crucial detail. Mercury breaks this rule completely. It is an iron ball masquerading as a planet. While Earth's core makes up about 17% of its total volume, Mercury's core accounts for nearly 60% of its volume and roughly 70 to 80% of its mass. The rocky mantle, the shell of stone that surrounds the core, is vanishingly thin, perhaps only 400 kilometers deep. If you were to slice Mercury in half, it would look less like a peach, with a pit, flesh, and skin, and more like a cannonball coated in dust. This composition is baffling because there is no known way to form a planet with this ratio of iron to rock directly from the solar nebula. If Mercury formed from the same cloud of gas and dust as Earth and Venus, it should have gathered much more rock. The raw materials were there. The physics of accretion should have piled up silicates on top of that iron core. So, why didn't they? This is where the zero Mercuries problem comes into play. When researchers like Sean Raymond run computer simulations of planet formation, they input the conditions of the early solar system and let gravity do the work. They run these simulations thousands of times. They get Earths, they get Venuses, they get Mars-like planets, but they almost never get a Mercury. In the rare instances where a planet does form at Mercury's distance, it usually ends up with a composition similar to Earth. It doesn't end up as an iron super-dense sphere. The simulations suggest that to get a Mercury, you need something to go wrong. You need a deviation from the standard process. This has led scientists to a startling conclusion. Mercury likely didn't start out this way. The prevailing consensus is shifting toward the idea that Mercury was once much larger. It may have been a proto-Mercury with a mass twice what it is today, perhaps even comparable to Mars. It likely had a thick, healthy mantle of silicate rock just like its neighbors. It was a normal planet, forming in a normal way. And then it was destroyed. Or at least partially destroyed. Something stripped away the outer layers of the planet, leaving behind the naked, dense core that we see today. This isn't just a process of erosion, it is a process of planetary amputation. We are looking at a survivor, a planetary remnant that has endured a trauma so severe it altered its fundamental structure. But what kind of force could strip a planet of its mantle? What mechanism is powerful enough to peel a world like an orange? There are a few suspects. One is the Sun itself. Perhaps the young Sun was far more active and violent than it is today, blasting the inner solar system with intense heat and solar wind that vaporized Mercury's outer layers. This is the vaporization hypothesis. It suggests that Mercury formed from iron-rich material because the rock simply couldn't survive the heat or was boiled off after formation. However, this theory has holes. Vaporizing rock requires temperatures of thousands of degrees sustained for millions of years. While the young Sun was active, it's unclear if it could have done this much damage. Another possibility is migration. Maybe Mercury didn't form where it is now. Maybe it formed further out, in a region where materials were different, and then migrated inward. But migration models usually result in the planet accreting more material, not losing it. This leaves us with the most dramatic and violent option, a collision. Before we dive into the catastrophe that might have created Mercury, I want to hear from you. Do you think it's possible that there are other stripped cores floating around our galaxy, or is Mercury unique? Drop a comment below with your thoughts. The collision hypothesis is currently the front runner. It suggests that the early solar system was a cosmic billiard table, with protoplanets smashing into each other at terrifying speeds. In this scenario, Mercury was a victim of a hit-and-run or perhaps a head-on crash that blasted its mantle into space, leaving the core behind. But even this theory faces a massive hurdle. If you blast a planet's mantle into space, where does the debris go? Gravity is a harsh mistress. Debris tends to reaccrete. It falls back onto the planet. So, even if Mercury was smashed, it should have gathered its pieces back up and reformed as a normal planet. Unless something else happened, unless the hit was so specific, so precise, and so energetic that the debris was carried away forever. In the next chapter, we are going to reconstruct this crime. We will look at the giant impact scenario and the hit-and-run theory. We will visualize two worlds colliding at 100 kilometers per second and ask the question, was Mercury the victim or was it the bullet? We have established that Mercury is a dense iron core wrapped in a thin shell of rock, a structure that defies standard formation models. We have established that it likely started as a larger planet that lost its outer layers. Now, we must ask, how? How do you skin a planet? The answer, according to leading planetary scientists like Alessandro Morbidelli, lies in violence on a scale that is hard for the human mind to comprehend. We are not talking about an asteroid impact like the one that killed the dinosaurs. We are talking about a collision between planets. This is the giant impact hypothesis. Imagine the early solar system, roughly 4.5 billion years ago. It is a chaotic shooting gallery. Dozens, perhaps hundreds, of protoplanets are jostling for position. In this version of history, Mercury was a fully formed world, perhaps the size of Mars, with a normal, rocky mantle. Then, disaster struck. A large object, another protoplanet, perhaps nearly as big as Mercury itself, slammed into it. The energy release would have been apocalyptic. We are talking about collision velocities potentially exceeding 100 kilometers per second. For context, a high-velocity rifle bullet travels at about 1 kilometer per second. Multiply that energy by the mass of a planet, and you have a cataclysm that turns rock into vapor instantly. In the classic giant impact scenario, this collision blasts the outer rocky layers of Mercury into space. The heavy iron core, being denser and deeper, survives relatively intact. The lighter silicate mantle is pulverized and ejected into a vast cloud of debris. But here is the problem we touched on earlier: gravity. Normally, that debris cloud would orbit the remnant core and eventually rain back down, reforming the planet. This is likely how our moon formed. Earth was hit, debris was thrown up, and it coalesced into the moon. So, why didn't Mercury reform? This brings us to a refined version of the theory, the hit-and-run scenario. Proposed by researchers like Eric Asfog and Andreas Reufer, this model suggests that Mercury wasn't just hit, it was sideswiped. Or perhaps Mercury was the impactor. Imagine Mercury as a projectile, slamming into a larger body, maybe proto-Venus or even proto-Earth. But instead of sticking, it grazed the target. The shock of the impact would strip away Mercury's outer layers, leaving them behind to be absorbed by the larger planet. The dense core of Mercury, stripped of its shell, would careen off into space, a naked, wounded world. This hit-and-run model is elegant. It explains where the missing mantle went. Venus or Earth ate it. It explains why Mercury is so small and dense. It fits the chaotic nature of the early solar system. So, what does this actually mean? It means that Mercury might be the shrapnel of a planetary war. It implies that the inner planets we see today, Mercury, Venus, Earth, Mars, are just the survivors of a much larger population of bodies that destroyed each other. However, there is a catch, a big one. If Mercury suffered such a catastrophic high-energy impact, an event that melted its surface and stripped its mantle, the planet should have been heated to extreme temperatures. The entire surface would have been a magma ocean. Any volatile elements, substances that vaporize easily, like water, potassium, sulfur, and chlorine, should have been baked out of the rock and lost to space forever. A Mercury born of fire should be a dry, dead, refractory cinder. It should be composed only of the most heat-resistant materials. But when NASA's Messenger spacecraft arrived at Mercury in 2011, and as BepiColombo confirms today in 2026, that is not what we found. We found the impossible. We found volatiles, lots of them. Messenger detected high abundances of potassium, a moderately volatile element. It found sulfur. It found chlorine. And most shockingly, it confirmed the presence of water ice, actual frozen water hidden in the permanently shadowed craters at Mercury's poles. This contradicts what we previously thought. If Mercury was stripped by a giant impact, how did it keep these fragile elements? How does a planet survive a collision that rips off its skin, yet retain the chemical equivalent of a delicate perfume? This is the volatile paradox, and it is the single biggest flaw in the giant impact theory. Some scientists argue that the volatiles were delivered later by comets and asteroids crashing into the cooling Mercury. Others suggest that the impact wasn't as hot as we think, or that the volatiles were trapped deep in the core and outgassed later. But none of these explanations are fully satisfying. The sheer abundance of volatiles suggests they are native to the planet, not just a dusting on top. So we are left with a contradiction. The density says giant impact. The chemistry says gentle formation. Can both be true? Or is there a third option we haven't considered? In the next chapter, we will explore this volatile paradox in detail. We will look at the planetary scars identified in late 2025 and the strange hollows on Mercury's surface, where rock seems to be sublimating into space right now. We will try to reconcile the fire with the ice. The story of Mercury so far has been a story of violence. We have painted a picture of a world born in chaos, stripped of its mantle by a cataclysmic collision, and left as a dense, iron-heavy remnant orbiting dangerously close to the Sun. But science is rarely a straight line. Just when the giant impact theory seemed to solve the riddle of Mercury's density, the planet itself offered a rebuttal. And it did so with the most unexpected evidence possible: chemistry. This is the volatile paradox. Volatiles are elements and compounds with low boiling points. Things like water, carbon dioxide, nitrogen, potassium, sulfur, and chlorine. In the context of planetary formation, they are the first things to disappear when things get hot. If you heat a rock to thousands of degrees, as would happen in a planet-shattering collision, the volatiles should vaporize and escape into space. Therefore, if Mercury formed via a violent high-energy impact, it should be dry. It should be depleted of potassium and sulfur. It should be a barren clinker of high-temperature ceramics and iron. But it isn't. When NASA's MESSENGER mission orbited Mercury, its gamma-ray and neutron spectrometer returned data that shocked the team. It found potassium, it found sulfur, it found sodium. The ratios of potassium to thorium, a standard measure of volatile abundance, were comparable to those of Mars, a planet that formed much further from the Sun and presumably suffered far less heating. This contradicts what we previously thought. In fact, it blows the giant impact theory wide open. As planetary scientist David Rothery has remarked, while it is clear that Mercury is rich in volatiles, we still do not know exactly which ones dominate or how they were retained. But the fact that they are there at all is a smoking gun that points away from a hot, catastrophic origin. And then there is the water. In the permanently shadowed craters of Mercury's north and south poles, places where sunlight has not reached for billions of years, temperatures remain at a frigid minus 180 degrees Celsius. Radar observations from Earth, later confirmed by MESSENGER, detected bright reflections in these craters. The signature is unmistakable: water ice, billions of tons of it. Now the water ice might be a later addition, delivered by comets impacting the surface over eons. That is a plausible explanation. But the potassium and sulfur? Those are baked into the crust. They are part of the planet's fabric. So we have a deadlock. Evidence A, density, says, I was stripped by a massive, hot collision. Evidence B, chemistry, says, I was never heated to extreme temperatures. How do we resolve this? Scientists are scrambling for new models. One proposal is that the impact was a hit and run that was incredibly fast but surprisingly cold, stripping the mantle mechanically without heating the deep interior. But physics makes that hard to swallow. Friction generates heat. Another theory, gaining some traction, is that Mercury formed from a special class of building blocks, oxygen-depleted, iron-rich meteorites known as enstatite chondrites or obrites. In early 2025, researchers like Camilla Cartier began analyzing obrite meteorites with renewed interest. These rare rocks have chemical signatures that resemble Mercury's surface. If Mercury formed from a swarm of these bodies, it might explain the chemistry without needing a giant impact. But it doesn't fully explain the density. You still need to get rid of the rock to leave that massive iron core. Perhaps the answer lies in the planetary scars identified in December 2025. These are massive ancient impact structures that are so large they theoretically should not have survived. They suggest that Mercury's crust is older and more resilient than we thought. If the crust survived the stripping event, maybe it acted as an insulator, protecting the volatiles inside. Or maybe, just maybe, our understanding of volatiles in planet formation is wrong. Maybe high-pressure environments can hold onto sulfur and potassium in ways we haven't modeled yet. This is where the BepiColombo mission becomes critical. Scheduled to enter orbit in November 2026, BepiColombo carries instruments far more sensitive than messengers. It will map the mineralogy of the surface in unprecedented detail. It will look for specific volatile species that can tell us the temperature history of the planet. It will also study the hollows, strange, bright, shallow depressions on the surface that look like Swiss cheese. These features appear to be young, suggesting that Mercury is still losing volatiles today. The rock is literally sublimating, turning into gas and drifting away. If BepiColombo can tell us what is evaporating from these hollows, we might finally identify the mystery component that has preserved Mercury's volatiles for 4.5 billion years. The volatile paradox is the key to the whole mystery. If we can solve it, we don't just explain Mercury. We explain how water and life-giving elements survive the violent birth of planets throughout the galaxy. In our final chapter, we will look ahead. We will discuss what BepiColombo might find in late 2026 and how this tiny, impossible planet is reshaping our search for Earth-like worlds around other stars. We have journeyed from the scorching surface of Mercury to the violent chaos of the early solar system. We have confronted the density dilemma and the volatile paradox. We have seen how this tiny planet defies our models, challenging the very rules of how worlds are made. Now, we look to the future. We are standing on the precipice of a new era in Mercury exploration. The joint European-Japanese mission, BepiColombo, is on its final approach. After a 7-year odyssey through the inner solar system, performing gravity-assist flybys of Earth, Venus, and Mercury itself, the spacecraft is scheduled to enter orbit in November of this year. This is not just another satellite. BepiColombo is actually 2 spacecraft in one, the Mercury Planetary Orbiter, MPO, and the Mercury Magnetospheric Orbiter, MMO. They will separate upon arrival, working in tandem to perform the most comprehensive investigation of the planet ever attempted. Why is this mission so important? Because it has the tools to break the deadlock we've been discussing. Messenger, the NASA mission that ended in 2015, gave us the first good look. It posed the questions. BepiColombo is designed to answer them. It will map the gravity field of Mercury with extreme precision, allowing us to see inside the planet and determine the size and state of its massive iron core. Is it fully liquid? Is there a solid inner core like Earth's? The answer will constrain the cooling history of the planet and help validate or rule out the violent collision theories. It will analyze the surface composition with higher resolution, zooming in on those mysterious hollows and the planetary scars identified in 2025. If BepiColombo detects specific volatile signatures in the exosphere, the thin wisp of gas surrounding the planet, it could tell us exactly what materials are sublimating from the surface. But the implications of this mission extend far beyond our own solar system. Mercury is a proxy. It is a laboratory for understanding super-Earths and sub-Neptunes found orbiting other stars. As we established, astronomers have discovered thousands of exoplanets. Many of them are hot terrestrials, rocky worlds orbiting very close to their host stars. Some have densities even higher than Mercury's, suggesting they too are stripped cores. If we can figure out how Mercury formed, we gain a blueprint for understanding these distant worlds. Is Mercury a rare fluke, a 1 in a billion cosmic accident? Or is the stripping of planetary mantles a common process in the universe? If the giant impact theory is correct, it suggests that solar systems are violent, chaotic places where planets frequently destroy each other. If the migration or vaporization theories are correct, it suggests a more orderly, albeit extreme, evolution. Mercury holds the answer. By studying this anomalous world, Scientists hope not only to solve Mercury's own mysteries, but also to better understand the growing population of exoplanets that resemble it. We are building a reference framework. When the James Webb Space Telescope or the Future Habitable Worlds Observatory looks at a rocky exoplanet, the data from Mercury will help us interpret what we are seeing. Although future missions may one day include landers or sample return efforts, perhaps bringing back a piece of that enigmatic, dark surface, for now, BepiColombo represents humanity's best opportunity to unravel the origin of a planet that, by all conventional logic, should never have existed. Mercury is a reminder that nature is more creative than our simulations. It teaches us humility. It shows us that even in our own backyard, there are worlds that break the rules. As we wait for November 2026, the scientific community is holding its breath. The data that streams back from that little iron world might rewrite the textbooks. It might tell us that our solar system is unique, or it might tell us that we are just one outcome of a universal process of destruction and creation. So, what does this actually mean for you? It means that the ground beneath your feet, the Earth itself, is part of this same violent story. The processes that stripped Mercury may be the same ones that gave Earth its moon or delivered the water in your glass. We are all connected in the great chaotic dance of gravity. If you've enjoyed this deep dive into the mystery of Mercury, please hit that like button. It helps this content reach more people who are curious about the cosmos. And don't forget to subscribe so you're here with us in November when BepiColombo finally arrives. Until then, keep looking up. The universe is full of surprises, and the biggest one might be right next to the sun.